Hey there, ready to dive into something truly mind-blowing? Imagine this.
Okay.
Planets beyond our solar system, orbiting distant stars.
Yeah.
Maybe even with oceans and continents like our own.
Wow.
We're talking about exoplanets, and today's deep dive is focused on a particularly fascinating type.
Yep.
Those orbiting the most common stars in the universe.
Right.
M-dwarfs, sometimes called red dwarfs.
Yeah. What makes this so exciting is that if we find habitable planets around these M-dwarf stars, it completely changes the game in terms of the potential for life in the universe.
Okay, so the sheer number of these stars is already intriguing.
Right.
But to make things even more interesting, there's been some groundbreaking new research using data from the James Webb Space Telescope.
Wow.
The JWST.
Okay.
This research is focused on the atmospheres of these exoplanets and whether they could actually support life as we know it.
So one of the key systems we're looking at is TRAPPIST-1,
Okay.
about 40 light years away.
Wow.
It's got multiple rocky planets huddled around a cool, faint M-dwarf star.
Now, I remember when TRAPPIST-1 was first discovered, everyone was buzzing with excitement about the possibility of finding life there.
Yeah.
But then some initial studies threw a bit of cold water on those hopes.
Right, because these M-dwarf stars, although common, are known for their intense bursts of UV radiation. Scientists were worried that this radiation could literally strip away a planet's atmosphere, leaving it a barren, airless wasteland.
So basically, imagine a planet starting out with a nice, cozy atmosphere and then having it blasted away by its own star.
Exactly.
Not exactly a recipe for a thriving ecosystem.
Exactly. But here's where things take a fascinating turn.
Oh, yeah.
This new research published in Nature Communications challenges that whole assumption about M-dwarf planets being automatically uninhabitable.
Okay.
They used computer models to simulate how a rocky planet's atmosphere evolves over millions of years, starting from a molten state and gradually cooling down.
Hold on. I'm picturing a planet fresh out of the cosmic oven,
Yeah.
all molten and fiery. How do they even begin to simulate something like that?
Well, these models are incredibly sophisticated. They factor in everything from the planet's initial composition and distance from the star to the intensity of that star's radiation.
Okay.
It's like creating a virtual planet and watching it evolve over eons.
So they fast forward through millions of years of planetary evolution
Right.
and see what happens to the atmosphere. What did they find?
Here's the kicker for planets in the Goldilocks zone. Not too hot, not too cold, but just right for liquid water.
Okay.
Something remarkable happens.
Okay.
The hydrogen in the early atmosphere, which you'd expect to just get blown away, actually reacts with elements deeper inside the planet.
Now, when you say Goldilocks zone, you're talking about that sweet spot where temperatures are just right for liquid water to exist on the surface, right?
Exactly. And it turns out this Goldilocks zone isn't just about surface temperature. It's about the interplay between the planet's atmosphere, its interior, and the type of star it orbits.
Okay, so you've got this hydrogen reacting with elements inside the planet.
Right.
What kind of elements are we talking about,
Right.
and what happens when they react?
We're talking about elements like oxygen and iron, common building blocks of rocky planets.
Okay.
Now, when hydrogen reacts with oxygen, it creates water, which is obviously essential for life as we know it.
Right.
And when hydrogen reacts with iron, it forms iron hydrides, which are compounds that actually store hydrogen within the planet's interior.
Wait, so instead of all that hydrogen escaping into space, it gets locked up inside the planet?
Yeah.
The planet is creating its own hydrogen storage system.
That's a great way to put it. And here's why that's so significant. As the planet cools down and solidifies, some of that stored hydrogen can be released back into the atmosphere through processes like volcanic eruptions. But because it's now bound to heavier elements, it's much less likely to just escape into space.
So it's like those heavier elements are acting as anchors, keeping the hydrogen from floating away.
Right.
And this all leads to a more stable atmosphere overall.
Precisely. And this is happening on planets that were initially thought to be highly vulnerable to losing their atmospheres due to that intense UV radiation from their M-dwarf stars.
So this research is really making us rethink what we thought we knew about habitability, isn't it?
Yes.
It's not just about the distance from the star, but also about what's going on inside the planet.
Absolutely. Planetary evolution is far more complex than we initially realized, and this research really highlights the incredible resilience of some of these planetary systems. It's a real game changer in our understanding of what might make a planet suitable for life.
Okay, so this is all based on computer simulations.
Yeah.
But haven't we already gotten some data from the James Webb Space Telescope about TRAPPIST-1?
We have, but it's important to remember that the JWST has so far only been able to observe the hottest innermost planets in the TRAPPIST-1 system.
Okay.
Those are the ones that are definitely outside the habitable zone, and as expected, they do seem to lack substantial atmospheres. But the really exciting observations, the ones that could potentially confirm these new findings, are still to come.
Okay, so we've got this tantalizing possibility.
Yeah.
Rocky planets around M-dwarf stars, even those initially thought to be uninhabitable, might actually have the potential to hold on to life-supporting atmospheres for billions of years.
Exactly. And the James Webb Space Telescope, along with other upcoming telescopes, will be instrumental in confirming this. It's important to remember that we can only study a small number of these potentially habitable planets right now.
But the potential payoff is enormous, right?
Absolutely.
Imagine finding evidence of an atmosphere on a planet in the habitable zone of an M-dwarf star.
That would be a monumental discovery, a giant leap forward in our search for life beyond Earth.
This research raises so many questions for me, and I bet for you listening too.
Right.
What are the implications of potentially finding not just one, but multiple habitable planets around these common M-dwarf stars?
That's a question that scientists and philosophers have been grappling with for centuries. And we're finally at a point where we might be able to start providing some concrete answers.
And it all starts with understanding how these planets evolve and whether they can hold on to their atmospheres.
Right.
Let's delve a bit deeper into how these models work and what they tell us about the potential for life-sustaining atmospheres on these fascinating exoplanets.
Let's do that. These models are like a window into the distant past and future of these alien worlds.
Okay, so we're talking about these incredible computer models that can simulate the evolution of a planet over millions of years.
Right.
You mentioned earlier that these models are incredibly detailed.
They are.
What kind of information goes into creating these virtual planets?
Right.
And how do they actually work?
Think of it like building a planet from scratch.
Okay.
You start with the basic ingredients, the elements that make up a rocky planet, like iron, silicon, magnesium, oxygen, and of course, hydrogen.
So it's like a cosmic recipe.
Right.
But how do you know what the recipe is for these distant planets?
That's where things get really clever. Scientists use data from telescopes to study the light coming from the planet's host star. And by analyzing how that light is filtered through the planet's atmosphere during a transit, we can get clues about its composition.
You mean when the planet passes in front of its star from our point of view?
Exactly. And as the planet orbits its star, we can also measure tiny wobbles in the star's motion caused by the planet's gravitational pull.
Okay.
This tells us about the planet's mass.
Okay.
From the mass and size, we can estimate its density,
Uh-huh.
which gives us further clues about what it's made of.
So we're piecing together a picture of the planet's interior based on its effects on the star's light and motion.
Yes.
That's pretty amazing detective work.
It is, and once we have a good idea of the planet's composition, we can input that information into the model along with its distance from the star,
Okay.
the star's temperature and radiation output, and other factors.
And then we hit the play button and watch as our virtual planet evolves over millions of years.
Essentially, yes, the model calculates how the planet's interior surface and atmosphere interact and change over time.
Wow.
It's not just a static picture, it's a dynamic simulation that shows how the planet responds to its environment.
That's so cool. You've mentioned before that for planets in the Goldilocks zone, something interesting happens with the hydrogen.
Right?
Can you remind us what that is?
Of course, early in a planet's life, when it's still a molten ball of magma, hydrogen, being the lightest element, tends to escape into space. But for planets in the Goldilocks zone, some of that hydrogen gets trapped within the planet.
Okay.
Remember, this is the zone where temperatures allow for liquid water on the surface.
Right. But you're saying that even in this temperate zone, there's still a chance for hydrogen to escape.
There is, especially in the early stages. But here's the key finding from this new research.
Okay.
In the Goldilocks zone, the hydrogen that doesn't escape reacts with elements like oxygen and iron in the planet's interior.
So the hydrogen is getting locked up in chemical compounds.
Exactly. With oxygen, it forms water, and with iron, it forms iron hydrides.
Okay.
Essentially storing the hydrogen within the planet's mantle.
And why is this important for the atmosphere? It seems like what's happening inside the planet is having a big impact on what's happening outside.
It absolutely does. As the planet cools and solidifies, some of that stored hydrogen can be released back into the atmosphere through things like volcanic outgassing.
Okay.
But now, because it's bound to heavier elements, it's much less likely to just float off into space. It's like those heavier elements are weighing the hydrogen down.
So it's a bit like a slow-release system for building up a stable atmosphere.
Yeah.
The planet holds onto the hydrogen until it's ready to use it later.
That's a great way to think about it, and this is a game changer for our understanding of planets around M-dwarf stars. Previously, we thought that the intense UV radiation from these stars would quickly strip away any atmosphere,
Right.
making them unlikely candidates for hosting life.
But this research suggests that even with that harsh radiation, these planets might be able to hold onto their atmospheres for billions of years, potentially long enough for life to emerge and evolve.
Exactly. It's a remarkable example of how planetary systems can find ways to self-regulate and maintain conditions that might be suitable for life.
Okay, so all of this is based on models. Has the James Webb Space Telescope actually observed any atmospheres on TRAPPIST-1 planets?
The JWST has observed the innermost planets of the TRAPPIST-1 system, those closest to the star, but those planets are too hot to be in the habitable zone.
So we're still waiting for JWST to take a look at those planets further out, the ones that might actually be in the Goldilocks zone.
That's right, and that's what makes this research so exciting. It provides a framework for interpreting those future observations. If we do detect atmospheres on the TRAPPIST-1 planets in the habitable zone, this research tells us that those atmospheres could potentially be stable and long-lived.
Okay, I'm on the edge of my seat here. It sounds like we're about to enter a whole new era in our understanding of exoplanets and the potential for life beyond Earth.
We are, and the James Webb Space Telescope is going to be at the forefront of these discoveries.
So what exactly will the JWST be looking for when it observes these planets? How can it tell us whether an atmosphere is present and what it's made of?
That's a great question, and it takes us into the fascinating realm of spectroscopy, the study of how light interacts with matter.
Okay, you mentioned spectroscopy. I remember learning a bit about that in school.
Yeah.
But it's been a while.
Yeah.
Can you give us a quick refresher on what spectroscopy is and how it helps us study exoplanet atmospheres?
Spectroscopy is like taking a rainbow and putting it under a microscope.
Okay.
You're essentially spreading out the light from an object, like a star or a planet, into its individual colors or wavelengths.
So it's like a cosmic prism.
Exactly. And by analyzing the pattern of these colors, we can figure out what the object is made of. Different elements and molecules absorb and emit light at very specific wavelengths, leaving a unique fingerprint on the light that reaches us.
So if we look at the light passing through a planet's atmosphere, we can see these fingerprints and figure out what gases are present.
That's the idea. Imagine the starlight passing through the planet's atmosphere. Like shining a flashlight through colored glass. The glass absorbs certain colors and lets others pass through. By analyzing the colors that are missing or dimmed, we can infer what kind of glass or atmosphere the light passed through.
So if we see the fingerprint of oxygen or water vapor, that's a pretty good sign that the planet might be habitable.
It's a piece of the puzzle for sure. But it's important to remember that finding a specific gas doesn't automatically mean a planet is teeming with life. Venus, for example, has a thick atmosphere with carbon dioxide, but it's a scorching, hot, hellish place.
So it's not just about finding the right ingredients, but also about the right proportions and the right conditions for life to thrive.
Exactly. It's about understanding the whole picture. The interplay between the atmosphere, the surface, and the star, and that's why this new research is so important. It gives us a framework for thinking about how these complex systems interact and evolve over time.
Okay, so to bring it all back, this research is telling us that rocky planets around M-dwarf stars, which are the most common type of star in the galaxy, might be able to hold onto their atmospheres for billions of years. Even with the intense UV radiation. And this is because of some fascinating chemical reactions happening inside the planet that essentially trap hydrogen and then slowly release it back into the atmosphere, creating a more stable environment.
It's a paradigm shift in how we think about habitability, and it opens up so many new possibilities in the search for life beyond Earth.
It's like suddenly realizing that there might be a whole lot more potentially habitable real estate out there in the universe than we previously thought.
Exactly. And the most exciting part is that we're on the cusp of being able to test these ideas with the James Webb Space Telescope. The data we're starting to get from JWST is already revolutionizing our understanding of exoplanets.
Right.
And we're only just beginning to scratch the surface.
And, even if we don't find definitive proof of life on another planet, just the act of searching, of pushing the boundaries of our knowledge and understanding is incredibly inspiring.
I couldn't agree more. It's a testament to human curiosity, our drive to explore and understand our place in the cosmos.
Yeah.
And who knows what incredible discoveries await us in the years to come.
So to our listener, if you find yourself gazing up at the night sky and wondering if there are other beings out there looking back at us, remember that the answer might be closer than we think. And the quest to find out is one of the most exciting adventures in human history.
Keep looking up and keep asking questions.
Thanks for joining us on this deep dive into the fascinating world of exoplanet atmospheres. If you're eager to learn more about this groundbreaking research, we'll be sure to include a link to the full article in Nature Communications in the show notes.
Until next time.